Hello, I am Patricio Whittingslow. Thank you for that introduction, and welcome to my talk. Little disclaimer, all views and opinions are my own. So there's a little bit to be said about me. I like simulating physical phenomena. I work on embedded systems professionally, and I regularly contribute to a few tiny projects in the Go ecosystem. And this talk is called Go in the Smallest of Places. When I say Go, I refer to the Go programming language. When I say smallest of places, I'm referring to microcontrollers, or MCUs, uh, also known as MCUs. If you've been to the TinyGo hack session, you may have seen a couple of these MCUs in action. We'll look at more MCU examples throughout the talk. Now, I want to leave this clear. This is a slightly ambitious talk. I want to paint a picture on embedded systems. I want to tell part of the history of why we develop in C today, and a little glimpse of promising new languages in this space. But I also don't want you all to leave without some meaningful knowledge of what developing for a microcontroller means. So hang on. Let's start with some history. In the beginning, there was assembly, and it was good. Around the 1960s, people started building bigger than usual stuff with assembly. The Apollo project, $182 billion in today's money, employed 400,000 people with the support of 20,000 industrial firms and universities. Huge project by today's standards, and largest single investment in times of peace. This is the Apollo Guidance Computer. I'll refer to it as the AGC. It is the computer that got us to the moon in 1969. The AGC is not a microcontroller by definition. It's missing the micro part, but it is one in spirit and functionality. The AGC would take orders from the humans aboard and respond to sensor inputs to control engines, antenna direction, among other actuators. This is a textbook example of an embedded system, a computer designed to perform a specific function within a larger mechanical system. Some of you may be familiar with this picture. That's Margaret Hamilton standing next to the entire AGC software in print. She was the director of the team that built the onboard flight software that ran on the AGC. She was arguably the first software engineer. She named the discipline, and let me tell you, if anyone's earned it, it's her. And next to Margaret's picture up on the slides is the front page of a manuscript which tells of the first conference on software engineering, organized by none other than NATO. In light of a rapidly shifting landscape, where larger and larger software was being developed, NATO brought the brightest minds in software engineering together. The objective was to discuss a worried state of affairs. Great minds like Alan Perlis, Edsger Dijkstra, among others, were present. Oh, that's a little. So, the conference paper is a great read. Up there are a few quotes from it. Many ideas are still relevant. Put simply, these fellas wanted to find better ways to develop software, especially when it comes to large software, and doubly especially when it comes to large software written in assembly, like the one you'd find on the AGC. People were still figuring out how to handle errors such that large systems wouldn't fail altogether. You gotta remember, the code was much harder to read. The Apollo guidance computer was programmed in an assembly for the AGC and a separate, higher-level interpreted assembly that was created to aid programmers developing trajectory control routines. What I'm showing you is the higher-level assembly. It's not quite Python. Code is available on GitHub for all you space nerds under Chris Gary's Apollo 11 repository. Alright, so let's fast forward a couple of years. Some wise guy develops a new language around 1972. That language was C, and it was based on several previously existing languages, and it was wonderful. It melded low-level concepts of assembly with the delights of a higher-level language, all with this Spartan syntax. We now could write these succinct programs that would have taken laborious work in assembly without compromising too much on the low-level control. And it was so readable. I mean, look at this. Back then, it felt and was nothing less than the language of the gods. And it still is today. C is proven and is still the first choice for new projects in the automotive and aerospace industry, where software is safety critical. C is also the lingua franca for most computers, your phone, laptop, be it Windows, Mac, Linux, or Android, uses C at the core. Our Go, Python, and Rust programs still have to talk to C to get stuff done, whether we like it or not. And so, to this day, it's all C, baby. Now and forever. Until now. Until now? So, C is great. It has some drawbacks. This is not a talk to delve into these topics. I will say, with every passing generation of new languages, C is replaced in gradually lower and lower level tasks. And in the last decade, we have seen a new generation of languages show promise in alleviating C's load. There are plenty of languages, but I will focus on 3. First up, Zig. And boy, does this language have an impressive resume. It's got comp time, revolutionary concept, explicit allocators, a built-in C++ compiler, an LLVM backend replacement in the works? Like, what? Zig shows some great promise. And next up, Crablang. This language memories management revolutionized how many think about software. Whereas C's const is famously mutable, Crablang makes variables immutable by default. There's several companies using Crablang in the low level, such as Oxide. Amazing stuff happening there. And it's the first language to take a shot at replacing C in the Linux kernel. So it's got something going for it. Then there's Go. It's okay, I guess. It's got memory safety, but you can hardly call yourself a language nowadays without it. Go was not designed to be a language to replace C in embedded systems. That much is clear. A garbage collector, which makes it a non-starter for some real-time projects. It requires a runtime, which already weighs like 1 megabyte when you're writing your first Hello World program. That's already tens of times larger than what's available on most MCUs. And a heavy dependence on the operating system. So yeah, Go's not ideal. But that's why TinyGo exists. We write Go, but use a different compiler, and this basically solves the aforementioned problems. You can practically remove the runtime from the binary entirely if you so wish to. In which case, you develop using some memory-safe C lookalike. And in my experience, Go's standard library in some cases is much closer to the metal than C's. So, let's talk on some takeaways. I didn't have to explain why people wanted to switch from assembly to C. That's self-evident. Now, do people want to write C forever? Yes, no, maybe so. No. Me, your cat, and the NSA say no. With that out of the way, microcontroller units, the quintessential piece of any embedded system. Let's look at how we can use Go in the lowest of low level by doing some memory mapped I/O. In doing this, I will disprove that one Reddit comment that just keeps popping up, I keep seeing it, something along the lines of, Go can't be used in embedded systems, or Go is only for web tooling and backend. Just to be clear, I didn't write this talk to post it as a video response to all these comments. No. That little black square you see on that printed circuit board is a microcontroller unit. We program it to execute code and control an embedded system. Let's take a closer look at that embedded square. So, zooming in, most space is actually empty, composed of copper paths and unbelievably thin wires which connect them. In the very center of the MCU is the functional bits. Raspberry Pi themselves had provided us with this map of the onboard functionality. How nice of them. And so there's an arrow pointing to a part of the MCU that is labeled the SIO, and it says process to GPIO. What's that? Well, GPIO stands for General Purpose Input and Output. A GPIO can control the voltage output of a pin and eventually turn a light on. That sounds like fun. Well, let's sit down and read the datasheet then and see how we'd interact with it. Logical next step. All right, so here's the page with the SIO, processor subsystem. The RP2040 processor subsystem consists of 2 ARM cores, blah, 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 blah. Aha, SIO. At the bottom of the page, the single cycle I/O block contains several peripherals that require low latency deterministic at blah, 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 blah. Okay, next page. Graphs, blah, 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 blah. Aha, GPIO control. This must be it. The processors have access to GPIO registers for fast and direct control of pins with GPIO functionality. Sounds like what we want to control an LED. Blah, 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 blah. Here's some code. So, one of these functions, written in C, sets the GPIOs, and the other clears them, which translates roughly to one turns them on and one turns them off. That's what we need to get the GPIO, the LED on. But this uses variables, which I don't have in my empty project, which I'm writing from scratch. It's also in C, and I don't want to write in C. I want it all in Go. We need more information. We need to know what these variables are, and we're not about to read C code, so blah, blah, blah. Here it is, the Rosetta Stone, or alpha and omega. This is it, the GPIO out register. It's offset 10 in hexadecimal, which is 16 in decimal. To turn the LED on, we'd have to write to this register. All right, we need 2 more pieces of data though. We need to know the base address of the SIO block, which if we click on that link in the PDF, takes us to the address of the SIO. And then we need to know what pin we're turning on, which on the Raspberry Pi Pico, the board I showed you earlier, is pin 25. So let's start programming it. So I wrote a small program that turns this LED on. I declare a pointer to the address of the GPIO out register and assign the desired value such that the voltage on pin 25 is high. There's an issue though. So the program is conceptually correct, but we need to write that bit shifted value to that address, but Go is uncooperative. This won't compile because Go is memory safe. We can't just define an address out of the blue and try to write to it unless we specify we are doing something dangerous. Let's write a function that takes an arbitrary address as a number and writes a 32-bit value to it. So this is the function we need. This code uses an unsafe package to declare a pointer to an arbitrary address and assigns to it. This code compiles and may perform a register write. I say may because it depends on how the compiler interprets our code. What I mean is, we are not writing standard code by this point. In the view of the Go compiler, this function just assigns to some piece of memory. It's not too different from assigning to a variable. However, this function, if called, would turn a light on. That's unheard of in Go. In normal Go, to change the state of our world, we would need to call a print function or perform an HTTP request, which interacts with the operating system, which carries out that task. In this, what we're trying to do is we're trying to be the operating system. So the issue here is if the Go compiler can prove that we never use the value we write to that address, it can optimize it out. As far as the Go compiler is concerned, nothing happened. This kind of memory we're assigning to is called memory mapped I/O, also known as volatile memory. TinyGo does have a package for dealing with this kind of memory, but we'll ignore that for now. So here we have a program that would seemingly do the requested register write in such a way that compiles, and this would maybe make our LED pin turn on, but it does not happen yet. In our excitement, we skipped over a few pages in the datasheet. So we go back, and here's the output enable register. Okay, we gotta enable that pin, I guess. Just set it. That's not enough though. We have configured the SIO block, but the SIO block is still not coupled to the copper. On closer examination, we see that we need to configure the connection to the copper pad to see the SIO block's output, and to do that, we need to configure the GPIO control registers of the LED pin. Do note we have to do some arithmetic since there's one register for each pin. So we won't be doing bit shifted values, we'll be doing some multiplication to get the register address, and this is what our LED program now looks like. So let's try it out. This wouldn't be complete without a live code demo. All right, let's augment the size of the font. That's our program. It's around 25 lines of code. Now I'm going to bring up the terminal. As you can see, I've been trying this out a lot, and I'm going to just go ahead and flash that program. I'm going to hold up the microcontroller, and you can see an LED turned on. All right. But I'm not satisfied. I'm not satisfied that easily. We're going to try to edit this code live. So what we're going to do is we're going to try to blink this LED. And we're going to use the time.sleep package, to sleep for a second between turning the LED on and off. And the way we turn the LED off, is by writing 0 to that register. And so this is, it's going to show y'all there's no tricks at play here. And okay, so we have a flashing LED. Yeah, all right. All right, I'm feeling good. Let's go back to the presentation. Okay, so keep in mind, TinyGo provides hardware abstractions. You don't have to program by writing to registers manually. Even Ron doesn't do that. TinyGo's pin type has a high and low method to turn an LED on and off. And the reason I'm showing you all of this is to give you a notion of how memory mapped registers work. Registers have an address, which we represent as an integer, and we write values to these registers, also an integer, to change the behavior of our system, much like you would change the behavior of a mechanical system by turning the valves. Understanding this concept is key to working with embedded systems. So, let me show you just how widespread this idea is. Let's look at the TinyGo drivers repository. This repo contains community-developed drivers for all kinds of sensors. If we were to search for the word register in this repo, we'd find 176 files with a match. That seems like a lot until you realize that there's only 120 drivers in this repository, with most consisting of 1 or 2 files. That means that almost every single driver has a concept of a register. The one difference between the MCU registers we just observed is that these drivers have registers that live off of the MCU silicon. We reach them via wires, where we communicate with protocols such as SPI, I2C, and WART. So, now let's look at a few places where you'd use MCUs with TinyGo. This is the Tiny Global project powered by TinyGo. It was built by Ron Evans using the Pico. And this Pico communicates via LoRa antenna and reports back telemetry. And it was released over Belgium and made its way over, to France with the help of 4 balloons. Next up is the Pico Lea. This board is running at Lea Aerospace's rocket testing facility. It measures flow rate, which is collected for post-firing analysis of the telemetry. And of course, it's rocking a Raspberry Pi Pico running TinyGo. And so far, I've shown you uses of the Pico pictured on the left. It might surprise you to know that the newest version of the Pico W, has an onboard Wi-Fi chip that can run an HTTP server written in Go. And if you were at the TinyGo hardware hack session, you may have one hanging from your neck right now. This is the culmination of 3 years of my work supporting the Raspberry Pi Pico's I/O in TinyGo, as well as writing a whole networking stack for use with microcontrollers. The links are in the slide. Thank you. Now, I see you all appreciate it, but some may ask, why? Why run bare bones Go on a Pico W when you have a perfectly fine Raspberry Pi 5 with Linux running on it? It's cheap. It's 10 times cheaper to buy a Pico W, and really that's enough reason for me. You also have much finer control of the code running on your machine. Don't pay for what you don't use, both in terms of memory and energy usage, and you get effortless build reproducibility since there's no environment or operating system. Now, one question remains. Actually, I'm about to close. We've looked at some history to understand why C is used in the industry. We've taken a look at the misconceptions about Go and embedded systems and where they stem from, and how TinyGo helps us write Go for MCUs without compromising performance. And we might feel more familiar around an MCU now that we know the code we write to interact with it is pure Go, no tricks, no makefiles. So what now? Did I give you all this knowledge so you could all go and start a flame war on Reddit of Go versus C? No. In the words of today's lightning speaker, Matthew Sanabria, build it. I want you to go. Go out there, buy a Pico, install TinyGo, and start blinking those LEDs. Stop waiting. Life goes by fast. We can wait for the perfect microcontroller to come along, but we'll miss out on the little things, like the Pico. Choose to live in the present and compile flash that program, because that Pico is good enough today, and because the journey to the destination is wonderful, no matter how small the place.